All right, so last time we talked about, we started with the unit circle and went through it in a kind of different way, probably than what you'd seen before, talking about its relationship with exponentials and complex numbers and how to view it. And then we went into even a little bit about how complex numbers cause rotations. And then we went into the unit hyperbola and talking about hyperbolic functions, and then we related them to exponentials too, except they don't have the imaginary components, they have the even and odd components. We showed how something we're going to do in the future, Taylor series, shows us how these equivalences we talked about with the exponentials come to be and how you can show that they are. And then the last thing I asked was for y'all to try this one. Anybody try this one? Okay, so what I did is I went ahead and I had written this out for you. So if you notice e to the I pi over 6, pi over 6 is that 30-degree one where the coordinates of the point on the unit circle are square root of 3 over 2 and 1/2. It's just that I made it square root of 3 over 2 plus I over 2 because the 1/2 is the sine component. And so it's I times sine, so it's I times the 1/2. That's where I got those numbers right there. And so I brought that down and said that's what e to the I pi over 6 is. And then I multiply it here by what 5 pi over 6 would be, which would be negative square root of 3 over 2 and then I over 2, because it would be negative square root of 3 over 2 and 1/2. All right, so the real and imaginary components. Now, if we multiply these together, we should get essentially -1. Because if we think about this conceptually, what we're saying is we start at we're starting at pi over 6 here, right? We're starting at pi over 6, this location right here, and we're going to rotate it by 5 pi over 6 right there. And so that should put us over here at the point -1, 0. So we should expect an answer like this: -1 in the real direction, 0 in the imaginary direction. And so let's try it real quick and see. We can see right here, if we multiply these two together, it's 5 pi over 6 times pi over 6. So that's 5 pi over 6 plus pi over 6. That's just pi. And so it's e to the I pi, which puts us right at the rotation of pi. All right, so there it works. And then on the other side, when we do this, we get square root of 3 over 2 times negative square root of 3 over 2. That's going to be -3 over 4. Then we have square root of 3 over 2 times I over 2. That's going to be plus I root 3 over 4. And then we end up with I times I over 2 times negative square root of 3 over 2. That's going to give us negative I root 3 over 4. So those two are just going to cancel out, right? A positive and a negative. And then the last one we have here is going to be I squared over 4. And if we look at that, we get -3 over 4, and then I squared is -1. So this becomes -1/4, which is -4/4, which is just -1. And then we have 0 in the I direction. And so there we end up getting it. See how it just actually took and rotated it by that amount. And so that's what that nice e to the I theta, you can cause rotations by that theta amount. Neat. And you could have thought of it the other way. We could have thought of rotating 5 pi over 6 by pi over 6. It still would have given us the same result, right? All right, any questions on that? Okay, so let's get into the actual hyperbolic functions here and what the graphs look like and how we can use them and stuff like that, not just the whole what are they, but what can we do with them? So here is a hyperbola. I drew this picture for you before. Hyperbolas can also, they can go like this too. If it's y squared minus x squared instead, it can be like that, but we're doing x squared minus y squared. So it'll look like that. It'll have a focus, vertex where it crosses that axis there, and you know, in a distance away from that center there. We have the asymptotes it goes to. You can also get this by slicing that double cone right there, and it'll give you a hyperbola as well. So Let's take a look at the basic hyperbolic functions. So let's look at this one. This is the sinh of x, the hyperbolic sine, and this is a sum of e to the x and then negative e to the negative x. So e to the x here, you can see over 2 gives you this nice exponential graph going up right here. Of course, it goes through 1/2 because we're dividing it by 2 and not through 1. So that's that exponential function right there. There, that's better. Right there, that's that exponential function. And then the other one is, first off, it's e to the negative x. So we have to take the reciprocal of it. The reciprocal of a function, if you're going to do that, anything that's at 1 stays 1, right? And that we're just talking about the reciprocal of e to the x. We're ignoring the 1/2 at the moment. Anything that's 1 stays 1. Anything that goes to 0 now goes to infinity. And anything that goes to infinity now goes to 0. So you see here on this side, we're going to infinity, which means in our reverse, we need to go to 0. Here we're going to 0, which means over here we now need to go to infinity. And here we'd be at 1, so we have to continue through 1. So it just kind of flips that one over around 1. We now also have to include this negative, which then flips it over the x-axis and gives us, once we include that negative, gives us this function. And then, of course, when we divide it by 2, it makes it go through 1/2 instead of through 1. And so there's the dotted line. That's that negative e to the negative x over 2. And then it's just the sum of the two. So here in the middle, we have negative 1/2 and 1/2. That's going to put us right at 0. As we go towards the positive side, this one goes to 0 and doesn't really have much of an effect. So we start to follow the e to the x graph right there and basically just get closer and closer to it. Then on the negative side, this one goes to 0, this one goes to infinity, so we follow this down here. And so you get that basic shape just from knowing what exponential graphs look like and knowing what our e to the x versions of the hyperbolic sine is. If you're not able to manipulate graphs like that, taking inverses of them and stuff like that and combining them together, something you want to practice. It's a good skill to have. Okay? Let's take a look at this one. Hyperbolic cosine, you can see we have e to the x and then plus e to the negative x. So we already just talked about those two. Here's the e to the x, and here's the e to the negative x right there, where the 0 went to infinity and the infinity went down to 0 when we did the reciprocal there. So you can see that as we add those two together, here we get 1/2 plus 1/2. That gives us the 1, so it goes through 1 there. And then everywhere else, this goes to 0 on the right, so it starts to follow just the e to the x one. The e to the negative x goes to 0 here, so it starts to follow just the other one right there. Okay, so it's just that combination of the two giving us that blue graph right there where you can see of the hyperbolic cosine. All right, any questions so far? Next, tangent and cotangent. Again, you can do this just by looking at, you can come up with tangent by doing the hyperbolic sine over the hyperbolic cosine, right? So you would be combining those two together. And so you get this basic shape here. But we also get, notice it goes between 1 and negative 1 there. But you can also do the inverse. Here it's going to 0. If it goes to 0, then it asymptotes up toward infinity at that 0 point. Zeros become infinities. Ones stay ones. And as this gets bigger, this gets smaller, right? And then you can do the same thing over here and get that basic shape. But then you have the blue one that is the hyperbolic tangent, and then the yellowish orange one there that is the hyperbolic cotangent. Okay? And then if you want to come look at the hyperbolic secant and hyperbolic cosecant, it is just a matter of looking at, like, hyperbolic secant is the reciprocal of the cosine. See, we have 1 here. Well, actually, I'll just draw the hyperbolic cosine. And the hyperbolic cosine, right, looks kind of like this. And as you can see, the 1 stays a 1 right there in the middle. And then as this goes up to infinity, this goes down to 0 and asymptotes to 0. All right, and the same thing over here, up to infinity, asymptoting to 0. And then for this last one, we're going to take the reciprocal of this graph right here. And so you can see it, you know, the previous graph was like that. So what we have happening is we have our 0 here, and notice both sides we're going, when we take the reciprocal, we're going to infinity, right? Going to infinity, going to negative infinity here. And then as this blows up to infinity, this goes to 0. Y'all see how I'm doing that? Ones stay ones, zeros become infinities, and infinities become zeros. Okay? And that's how you can kind of do that pretty quick. But anyway, there's a look at those graphs there. As long as you know that exponential graph, you should be able to figure any of these out, or which is the way I usually do it. Can't say I have all of these memorized. I just tend to go through and do them, but that's about it right there. Okay, whether it's memorize all these or, you know how to figure them out by memorizing 2 of them or 3 of them or whatever, and that's the way you should do it. Okay. All right, any questions on that? Okay, good. Moving on, let's see here. It says, use the definition and identities for the hyperbolic functions to evaluate and simplify. So let's take a look at this very first one. We have 2 times sinh of x times cosh of x. So I'm going to do this one, and then we'll work on the next one together. So we'll make this 2 times, and then we're going to replace it. So sinh is actually e to the x minus e to the negative x over 2. And the hyperbolic cosine is e to the x plus e to the negative x over 2, just like that. Okay, so you end up with a 2 over 4. And then we have e to the x minus e to the negative x times e to the x plus e to the negative x. So e to the x times e to the x is e to the 2x, just foiling here, right? And then I have e to the x times e to the negative x. That's just 1. And then I have e to the negative x, or negative e to the negative x times e to the x. That's negative 1. And then I have minus e to the negative x times e to the negative x. That's e to the negative 2x, just like that. The plus 1 and minus 1 will cancel. And the 2 over 4 becomes a 1 over 2. And so I end up simply here with e to the 2x minus e to the negative 2x over 2, which is just the hyperbolic sine of 2x. Yes?
The table at the bottom, are you going to have that in the text?
I don't know. I'll think about it. Personally, I think you should be able to figure those out, like we're doing right now. Like I just right there did one of these, the second one in particular, and it didn't take me but a couple seconds. Okay, I'll think about it. We'll talk about it when we get closer. But I highly recommend you be able to do that though, because you never know if you're going to have that with you or not. Especially since this is something you don't really have to memorize. You can figure out. Anything you can figure out, you should learn how to figure out. Okay, I'm of that opinion. Okay, next, cosh of 5x plus sinh of 5x. So tell me, what should I do here? Okay, so for the exponential, so what's the what do I write for the exponential of the cosh? Nope. There you go. There we go. See how we did that? There you go. And then plus, and then what? There we go. And now I have positive e to the negative 5x and negative e to the negative 5x. So what happens there? They cancel, right? A positive and a negative there. Excuse me. And so then that gives me what? E to the 5x plus e to the 5x is, yep, over 2. There we go. Mm-hmm. All right. This should make sense for us because, like you just said, I'm going to do t. E to the t is cosh t plus right? From our, where did we do that? Right there, or minus? No, right there, this one. What am I looking at the minus one for, right? Okay, good. So that works out for us. So like a check mark. Okay, take a look at this one. Natural log of cosh plus sinh plus the natural log of cosh minus sinh. So what should I do here? Anybody tell me what that equals? Nope. Nope. If it was subtraction, it'd be A divided by B. Okay. Right. I mean, think about it. When you multiply two exponentials together, you end up adding the exponents. So here, if we're adding the two inverse logs, we end up multiplying what we're taking the log of. You can go through and do that proof if you want, if you don't remember it. But yeah, that right there. So what should I do first? There you go. Like that. And y'all's favorite thing, the foiling, which I don't like to call it that, term by term multiplication, right? So what do I get? Not cosine. Okay. Is that it?
Minus sinh square of x.
Good. Is that it? Huh? No? What else? Yes, right there. There we're done, right? Because the cosh times sinh will have a negative quotient and they'll cancel out, right? Because it's a plus b times a minus b. All right. And what's cosh squared x minus sinh squared x? Nope. Oh, Patrick, not negative one. Yep, right, it's right here. Maybe I can let you have that on the test. That's our cosine squared plus sine squared equals 1, except here it's cosh minus sinh equals 1. So this is the natural log of 1. And what's the natural log of 1? No. 2. 0. Right? Right? Remember, this is log base e of 1 equals what? So it's asking us, if we take the exponential of both sides, we're essentially asking e to the what equals 1, and the answer is 0. There's our answer. There's our answer up there. That's our answer up there. Okay? Isn't this fun? Not really?
I think it is better than the integral application.
Oh, wait, we're about to do some more integrals. All right, so now we're going to go ahead and start doing the derivatives of hyperbolic functions. So we're going to start with the derivative of the hyperbolic sine. And how do you think we're going to do that?
The same code,
We're not jumping to what the answer is. How are we going to do that? What are we going to take the derivative of? Like that, right? We can bring that 1/2 out front, d dx of e to the x minus e to the negative x. What's the derivative of e to the x? Good. What's the derivative of negative e to the negative x? Huh? There you go. What? There you go. And so what's 1/2 of e to the x plus e to the negative x? Cool, huh? Derivative of sine is cosine. Derivative of sinh is cosh. Huh? Huh? Any guesses on what the derivative of cosh is going to be? Try it. Go ahead. I'll pause this for a minute. Y'all try. Quick. And it was easy to do. It was a cinch. That's in honor of Professor Tesla right there. Throw that out for everybody. All right, so this one is derivative of e to the x plus e to the negative x over 2. And then that's 1/2. Derivative of e to the x is just e to the x. And derivative of e to the negative x is minus e to the negative x. And that right there is sinh of x. Cool? All right. Let's take a look at this one. Maybe I'll do one of them and let you do the other. So let's take a look at this one. Let's walk through this one together. D dz of the natural log of the hyperbolic cosine of z. All right, and remember, this is all inside that, right? So what's the derivative of this guy going to be? So the derivative of the natural log is 1 over x. So what does this one become? We've got to do chain rule. So we do the derivative of the outer part. And so the derivative of the natural log part is 1 over what's inside the natural log times the derivative of what's inside the natural log, right? Then we have 1 over cosh z, and the derivative of cosh is sinh z, and sinh over cosh is tan z, I guess. I don't know. I don't know a name for that one. Hyperbolic tangent of z. Cool? All right, why don't y'all try that next one? What do you come up with for this one? agree with that. So here, let's write it out real quick. We can bring the 1/2 out in front, right? And then you do the derivative of the outer, which is the sinh one, and derivative of sinh is cosh 2x plus 1, and then times, then times the derivative of what's on the inside. The derivative of 2x plus 1 is just 2. That 2 cancels with that 1/2, cosh 2x plus 1. Okay, so now we know how to use those. Let's go on to the next page. And let's do some integrals. These should be not so bad, right? So think about this. d dx of cosh of kx is k sinh of kx, right? And d dx of sinh of kx is k cosh of kx, right? Chain rule. So what do we think the integral of sinh of kx dx is going to be?
Cosh.
So we're going to have some sort of cosh. That it? That it? We're missing something. Plus c. And if you want to try this one and really see it, you can do integral e to the kx minus e to the negative kx over 2 dx. Bring your 1/2 out front. Integral of e to the kx minus e to the negative kx dx. And then we've got our 1/2. And then the integral of e to the kx is 1 over k e to the kx. And the integral of the negative one is minus minus, so it becomes plus 1 over k e to the negative kx, right? Because we have that negative, so it's a negative, negative, positive. Okay, and then, and then plus c, which I guess doesn't have to be inside the brackets. And that right there is 1 over k cosh k x plus c. Pretty neat how it just keeps working out like that, isn't it? It just does not seem like these should be related to exponentials, but I mean, the more times we do it, the more it just keeps fitting and working out, doesn't it? All right. What about this one? Good. Okay. What about that one? Close. Can we use u substitution here? What would I have u equal? Right? So this is And what's that integral become? Not cosh x. And plus c. And then we can just substitute 5 cosh u was x over 5 plus c. Okay, I'm gonna let y'all try that next one too. That one of those new Amazon planes. No, I'm serious. Y'all try this one. That's what I got. Plus C. You're missing the 1/4 there somehow, right? Because you have that 1/2 there already. It shouldn't go anywhere. But when you do that integral of cosh 2x, right? Right up here. Or when we do those integrals, look, we're getting the 1 over k. Right? So if we just use that, or wait, what was this? This was cosh. So if we just use this result right here, right? This is, we've got a 1/2, and then we have our integral cosh 2x dx. And then according to this, that just equals 1 over 2 sinh of 2x plus a c. So this would be either, you can, I mean, you can write 1/4 sinh 2x plus c. You could go through and well, I mean, you're using the chain rule in reverse is what would get it to you. Is that what you did? You put a 2 out there instead of a 1/2? Yeah, because that's with integrating. So, or derivative. If it was the derivative of that, then you would have been correct. But it was the integral. Okay. All right. What's that answer?